Okay, now we continue on example 4 and 5. Okay, this example 4 and 5, we focus on NTU method. Okay, let's read the question first. A counter flow double pipe heat exchanger is to heat water from 20 degrees Celsius to 80 degrees Celsius at rate 1.2 kg per second. So the heating is to be accomplished by geothermal water available at 160 degrees Celsius at a mass of flow rate 2 kg per second. The inner tube of the inner tube is thin wall and has diameter 1.5 cm. The overall heat transfer coefficient is 640. Using the effectiveness NTU method, determine the length of the heat exchanger required to achieve the desired heating. So basically, this example is same like example 2. Sorry. So but this time we need to use NTU method. Okay, now first thing first, you need to calculate the heat capacity for the hot fluid and also cold fluid. So CH is equal to MH CPH. So previously we just used the specific heat capacity but for this time we need to calculate the heat capacity. So CH and CC, CCPC. Okay, given in the question for the hot fluid is 2 kg per second. Time with the CP that we obtained previously for the hot fluid is around, for geothermal water is 4.31, for the water is 4.18. So times it with 4.31 here, you get 8.62 kilowatt over Kelvin. So here we have a 1.2 mass flow rate times with 4.18, we get 5.02 kilowatt over K. Okay, so from here, like what I mentioned inside the previous video, the lecture video, we need to find the minimum heat capacity. So when we compare both heat capacity for hot fluid and also cold fluid, we can see that the minimum value for the heat capacity goes to cold fluid. So C min would be 5.02 kilowatt over K. So the maximum heat capacity would be Cmax B hot fluid heat capacity, which is 8.62 kilowatt over K. Okay, so we need to find first the capacity ratio Cmin over Cmax is equal to 5.02 over 8.62, 0.582. So we need to find next is heat transfer rate maximum, Qmax. So the formula is equal to Cmin times with TH in minus with TC in. Okay. So TH in minus TC in, 160 minus 20. So the answer would be 702.8 kilowatt. Okay. So this is the maximum possible heat transfer rate in the heat exchanger. So to calculate the actual heat transfer rate, we can use the formula of heat balance, which is MCP delta T. So we calculate for the water here. So mass flow rate for the water is 1.2. Cp for the water is 4.18. So T out minus T in. T out is 80 for the water minus 20 for the water inlet. So the answer would be 3010 kilowatt. Okay. So after obtaining the actual and also maximum heat transfer rate, we need to calculate the effectiveness of this heat exchanger. So the formula is Q actual over Q max. So the answer would be 0.428. So next we need to calculate, after obtaining the effectiveness, we can calculate NTU. So to calculate NTU, you can refer to this table 11.5. So we have a counter flow heat exchanger. Okay, we can take this one because we obtain the capacity ratio less than 1, right? So I continue here. NTU is equal to 1 over C minus 1 ln okay. Now we substitute the value 1 over. So for C just now, the capacity ratio is 0.582. Effectiveness is 0.428. So C 0.582 minus 1 ln effectiveness 0.428 minus 1 over with 0.428 times 0.582. Sorry, let me this here. So here minus 1. So the value of the NTU obtained is 0.651. So from here, like what I'm showing you into the lecture video, NTU is equal to UAS over C min. So now our objective is to find the area in order to know the length of the heat exchanger itself, and length of the tube inside the heat exchanger. Okay. So rearrange the equation. Substitute the value. So, oh sorry, this one is C. The value for C min is 5.02 kilowatt over K. So we convert to watt over K. Over with the value of U given 640. So we will get NTU, we will get AS, surface area 5.11 meter squared. Okay. So AS is equal to pi dl. So substitute the value of A and D. we can get L is equal to 1.08 meter. Okay. Okay, we can refer back to 11.4. Sorry, example 2 just now. We obtain the L. Sorry, this one basically the value is 1.09 meter. Let me check back. Yes, the value is 1.09 meter. Try to calculate by your own. Check with me whether my answer is correct or not. Oh, so sorry. Try to check back with this one and example 2. So let me calculate back. Example 2, 5.12 divided with by time with 0.015. Yes, we get around 109 meter. So this one is not point. So 109 meter. So basically, I wrongly calculated here. So let me check back. Give me a moment. Yes, here we obtain 108 meter. Basically, there is not so much difference when we use LMTT and also NTU. Okay. So now we move to example 5. So example 5 is on the cooling hot oil by water in a multi-pass heat exchanger. So basically, it's similar like example 4. We need to calculate the C min, Q max, NTU. So let's read the question first. Hot oil is to be cooled by water in a shell. One shell pass, 8 tube passes. Heat exchanger. The tube are thin wall and are made of copper with an internal diameter 1.4 cm. The length of each tube pass in the heat exchanger is 5 meter and the overall heat transfer coefficient is 310. Water flow through a tube at the rate of 0.2 kg per second and the oil through the shell at the rate of 0.3 kg per second. The water and the oil enter at the temperature of 20 degrees Celsius and 150 degrees Celsius respectively. Determine the rate of heat transfer in the heat exchanger. So rate of heat transfer Q and the outlet temperature of the water and the oil temperature. So we need to know these two parameter. So first thing first, we need to find the heat capacity of the water and also of the heat capacity of specific heat capacity of the oil. So Cp first. Cp water we will obtain 4.18. Cp for the oil is 2.13 kilojoule kg dot degree Celsius. So to calculate all of this, we need to use the NTU method. Why we don't use LMTD method? Because if you use LMTD method, you need to do a few steps of iteration. It can be quite complicated if you use LMTD method. So it's better for you to use NTU method. Okay, to use the NTU method, like what I'm saying in the previous example, you need to calculate the heat capacity. So CH is equal to MH, CPH is equal to, so I directly calculate this one. I got 0.639 kilowatt. Okay, so this one you just put the value. So this the mass flow rate for the hot oil is around 0.3 kg. For the cool water is 0.2 kg. So you will get here 0.836 kilowatt. Okay. So from here we can see this one is our Cmin. This one is our Cmax. So calculate the capacity ratio first. Cmin over Cmax. So the answer will be 0.764. So from here you can use Qmax formula. Cmin Th in minus Tc in. So this formula you can see inside my previous video for the lecture video. So this one you will get 83.1 kilowatt. Okay. So next step is to calculate the NTU, but before to calculate the NTU, you need to know the area of this heat exchanger. So the surface area is S time is equal to number of tube times with pi dl. So in the question given, we have this shell and tube heat exchanger consists of 8 tube passes. So put 8 here, pi 0.014 times with length is 5 meter. So you will have 1.76 meter square. So NTU, you can use this formula UAS over Cmin. So basically, if in the question given with the value of effectiveness, then you can use the formula that we use inside the example 4, the formula that we take from the table 5 just now. But basically, you can use this formula also. So U is 310, 1.762 over Cmin. So Cmin must convert into watt. So 639. The answer is 0.854. Okay, after obtain this NTU, you can calculate effectiveness. Previously, we used table 11.15 to calculate NTU. But remember, inside my lecture video, I give you the table 11.4 table. Inside there you have the effectiveness relation formula, so from that table you can use you can take that formula and calculate the value of effectiveness for the multipass heat exchanger. So I directly give the answer here. Effectiveness is 0.47. So to calculate the rate of heat transfer, you can times the effectiveness with Qmax. Basically, this question need you to calculate the actual rate of heat transfer. So 0.47 times with Qmax 3.1, you will get 39.1 kilowatt. Okay, so this is the first question. For the second question is outlet temperature of the water and the oil. So to calculate the outlet temperature, you can use the formula Q is equal to Cc. You can use the heat balance formula. Either you want to use MCP delta T or directly C times delta T. So this one is for water. So TC out would be TC in plus Q over Cc. So directly input TC in. TC in, we know that for the water is around 20 degrees Celsius. So 20 plus with 39.1 over Cc, 0.837. So the answer you will get is 66.8 degrees Celsius. So next we need to know, this one is for water. We need to know for the hot oil. So for the hot oil, I just directly use the formula. We just change it, this one, to TH out, TH in plus Q over CH. So TH in is 150. Oh, so sorry, this one. Okay, let me erase first. For the cold one, we use the difference of temperature TC out minus TC in. But for the hot one, we use the difference in temperature TH in minus TH out. So because the heat is transferred from the high temperature to low temperature. Okay. So TH out be equal to TH in minus with Q over CH. So substitute TH in 150, Q this one, and CH this one. You will get the temperature for the temperature out for the hot fluid is 88.8 degrees Celsius. Okay, so basically this is the method to calculate the heat transfer rate and also temperature outlet using NTU method. Okay, before I end this video, I want to go back to example 4 just now. So just now I mentioned to you, there's not much different in the length for the heat exchanger using NTU and LMTD. Basically, if you try to calculate, you will get this value 108.4 meter. But for example 2, you will get 108.67 meter. So basically the difference is not much. So that's why I said before the difference is not much. But if we run out, we can see there is a difference of 1 meter. Okay, so I hope you can understand to what I'm explaining from example 1 until example 5. If you get confused on any parameter that you want to calculate, or you didn't understand on what I'm explaining before, you can directly ask me through Telegram or WhatsApp. Thank you.